The discovery. On July 1st, 2025, a telescope in Chile spotted something moving through space at 61 kilometers per second. Within 24 hours, astronomers confirmed what they suspected. This object came from outside our solar system, and it brought with it secrets from the depths of interstellar space. The discovery happened at the Atlas Telescope Facility in Rio Hurtado, Chile. ATLAS stands for Asteroid Terrestrial Impact Last Alert System, and it scans the sky every night looking for objects that might pose threats to Earth. On this particular night, the automated system flagged something unusual. The object appeared faint with a magnitude of 18, meaning you would need a decent telescope to see it. But the really interesting part came from its speed and direction. At 3.5 astronomical units from Earth and 4.51 astronomical units from the Sun, this thing was moving faster than anything bound to our solar system should move. The Minor Planet Center initially listed it on their Near-Earth Object Confirmation page. Observatories around the world started pointing their instruments at this mysterious visitor. Within a day, they had 122 observations from 31 different sites. Something big was happening. Astronomers dug through their archives and found that other telescopes had actually captured images of this object weeks earlier without realizing what it was. The Zwicky Transient Facility had images going back to May 7, 2025. Even the Test Space Telescope had caught it between May and June. By July 2, 2025, the designation came through. This was C2025N1 discovered by ATLAS. But more importantly, it received the designation 3I. That I stands for interstellar. This was only the third confirmed object from beyond our solar system ever detected passing through. The first three interstellar visitors. The first interstellar visitor we found was 1I, better known as Oumuamua, back in 2017. That one looked more like an asteroid with no tail or visible coma. It had this weird elongated shape and tumbled through space in a way that sparked all kinds of debate. The second visitor, 2I, Borisov, arrived in 2019 and looked much more like a traditional comet with a clear tail. Now we had 3I Atlas, and it was already showing characteristics that made it unique among all three. Number 10, hyperbolic orbits explained. Coming in at number 10, we need to talk about what makes an orbit hyperbolic. Most objects in our solar system follow elliptical orbits, meaning they loop around the sun in closed paths. Their orbital eccentricity is less than 1. When an object has an eccentricity greater than 1, it follows a hyperbolic trajectory. This means it comes in from deep space, swings around the sun once, and heads back out into the galaxy, never to return. The eccentricity of 3I Atlas measured at 6.1394 with an uncertainty of just plus or minus 0.00003. This is an incredibly precise measurement, and it confirmed beyond any doubt that this comet originated outside our solar system. The orbit itself tells us a lot. 3I Atlas reached its closest point to the Sun, called perihelion, on October 29, 2025 at 11:36 Universal Time. This put it at 1.35653 astronomical units from the Sun, just inside the orbit of Mars. For reference, Earth orbits at 1 astronomical unit, so this comet came relatively close by cosmic standards. The inclination of its orbit measured at 175.11 degrees, which means it was traveling in a retrograde direction, moving opposite to the way planets orbit the Sun. When you account for the ecliptic plane, which is the flat disk where most solar systems objects orbit, it was tilted about 4.89 degrees. The hyperbolic excess velocity reached 58 kilometers per second. This number represents how fast the object was moving relative to the Sun after you subtract out the Sun's gravitational influence. At perihelion, its actual speed hit 68.3 kilometers per second. These speeds are faster than any previous interstellar object we've detected. Number 9, tracing the origin. Number 9 brings us to where this comet came from. By tracing the trajectory backward, astronomers calculated that 3I Atlas approached from the direction of the galactic center in the southern celestial hemisphere. The velocity components break down like this. U equals negative 51 kilometers per second, meaning it was moving away from the galactic center. V was positive, showing motion in the direction of galactic rotation. W measured plus 18.5 kilometers per second, indicating upward movement through the galactic plane. These numbers suggest the comet originated from either the thin disk or thick disk of our Milky Way galaxy. This southern origin challenged existing models. Most predictions expected interstellar objects to come from the northern solar apex direction, which is where our solar system is heading as it moves through the galaxy. Finding 3I Atlas coming from the south means our detection methods and expectations need updating. On October 3, 2025, the comet made its closest approach to Mars, passing just 0.1937 astronomical units away. That works out to about 29 million kilometers. Mars orbiters and even the Perseverance rover got to observe this interstellar visitor from a unique vantage point. For Earth, the closest approach happens on December 19, 2025, at a distance of 1.7981 astronomical units, plus or minus 0.0004 astronomical units. That puts it somewhere between 167 and 270 million kilometers away. There was never any danger of impact, but it gets close enough for extensive study. Number 8, physical characteristics of the nucleus. At number 8, the physical characteristics of the nucleus present some challenges to measure. When you look at a comet, you see a big fuzzy cloud of dust and gas called the coma, and maybe a tail. The actual solid nucleus is tiny by comparison, it's usually hidden in all that activity. For 3I Atlas, estimates put the nucleus diameter somewhere between 0.32 and 5.6 kilometers. The most likely size based on dust production rates and Hubble observations is under 1 kilometer. The Hubble Space Telescope set an upper limit of 5.6 kilometers based on how bright it could detect the nucleus to be. The rotation period clocks in at 16.16 hours, plus or minus 0.01 hours. Astronomers figured this out by watching how the brightness changed over time. As the nucleus spins, different areas reflect different amounts of sunlight. Initially, the brightness varied by 0.3 magnitudes, but as activity increased and the coma grew, this dropped by 0.2 magnitudes. The coma itself grew to impressive proportions, reaching up to 26,400 by 24,700 kilometers in an elliptical shape. That's bigger than Earth. The dust tail extended over 100,000 kilometers in the anti-solar direction. The color of 3I Atlas trends towards the red end of the spectrum. Spectral slope measurements in visible light showed 21.1 to 22.8% per micrometer in the blue to red range, flattening to 9.8% per micrometer in the red to near infrared. This makes it redder than most solar system comets, though some trans-Neptunian objects show similar colors. Interestingly, the color changed over time. Optical wavelengths showed increasing redness, while near-infrared showed a bluing effect. This evolution relates to changing dust properties and compositions being released as the comet heated up. Number 7, an unusual composition. Number 7 focuses on composition, and this is where things get really interesting. The James Webb Space Telescope observed 3I Atlas on August 6, 2025, and revealed a coma dominated by carbon dioxide. The mixing ratio of carbon dioxide to water measured at 8.0 plus or minus 1.0. In simpler terms, this comet was releasing about 8 times more carbon dioxide than water vapor. For typical solar system comets, this ratio usually sits around 0.12. Some comets have higher carbon dioxide, but not like this. Statistical analysis showed this enrichment was 4.5 standard deviations above the median for solar system comets. That is extraordinarily unusual. The production rates for different molecules paint a detailed picture. Carbon dioxide flowed out at 129 kilograms per second, plus or minus 1. Water vapor came off at 6.6 kilograms per second, plus or minus 0.2. Carbon monoxide added 14 kilograms per second, plus or minus 0.9. These were also emissions of carbonyl sulfide at 0.43 kilograms per second, plus or minus 0.09. Atomic nickel showed up at 4.6 grams per second, plus or minus 0.7. Cyanide radical emissions hit 17.6 grams per second, plus or minus 2. What the comet didn't have also matters. Carbon chain molecules like C2 and C3 were heavily depleted. Most comets showed these carbon chains prominently in their spectra, but 3I Atlas barely registered any. No iron emissions appeared in the data. The water ice grains were incredibly fine, smaller than 1 micrometer, and likely in an amorphous rather than crystalline state. Number 6, the role of galactic cosmic rays. At number 6, we need to explain why this composition is so weird. The answer involves galactic cosmic rays. These high-energy particles stream through interstellar space constantly. They come from supernova explosions, active galactic nuclei, and other violent cosmic events. When cosmic rays hit a comet nucleus floating through interstellar space, they deposit energy into the ice and cause chemical changes. Over millions or billions of years, this radiation processing transforms the outer layers. Models show that galactic cosmic rays convert carbon monoxide into carbon dioxide. The process works like this. A cosmic ray particle slams into the icy surface, breaking chemical bonds and creating reactive fragments. These fragments recombine in new ways. Carbon monoxide plus radiation equals carbon dioxide. The same process creates complex organic molecules and amorphizes crystalline ice into a disordered structure. For 3I Atlas, the cosmic ray dose in the outer layers reached approximately 5 times 10 to the 23rd power electron volts per cubic centimeter. This bombardment affected the outer 15 to 20 meters of the nucleus. Erosion removed less than tens of meters of material over the comet's lifetime, which means what we observe today is entirely this radiation process layer. We're not seeing pristine material from where the comet formed. We are seeing material that has been cooked by cosmic rays for anywhere between 1 and 11 billion years. Think about that age for a moment. Our entire solar system is 4.6 billion years old. 3I Atlas could be between 7.6 and 14 billion years old based on various age estimates. It might have formed before our sun even existed in some distant stellar system during the early epochs of our galaxy. Number 5, the Global Observational Campaign. Number 5 covers the Observational Campaign, which involved an unprecedented coordination of space-based and ground-based telescopes. The Hubble Space Telescope imaged the comet on July 21, 2025, providing early constraints on nucleus size and capturing the developing coma. The James Webb Space Telescope followed with its observations on August 6th, using sensitive infrared instruments to detect the molecular composition. These observations required careful scheduling because both telescopes are in high demand for many different science programs. Ground-based facilities contributed extensively. The Very Large Telescope in Chile conducted spectroscopy throughout July and August, detecting cyanide and nickel in the coma. The Southern African Large Telescope added additional spectroscopic data. Gemini South captured images showing tail growth and evolution. The Swift Space Telescope detected water and hydroxyl radicals. Sphere X noted an extended carbon dioxide coma beyond the main nucleus. NASA organized a multi-mission campaign involving nearly every available asset. The Lucy spacecraft, currently on its way to study Jupiter's Trojan asteroids, turned its cameras toward 3I Atlas and captured stacked exposures showing the misty coma. The Psyche mission, headed to a metal-rich asteroid, provided 4 different viewing angles. Stereo spacecraft, designed to study the Sun, caught the comet during its perihelion passage. SOHO, the Solar and Heliospheric Observatory, also observed it when it came close to the Sun. Punch, though still in commissioning, contributed ultraviolet data revealing hydrogen atoms in the extended coma. Mars-based assets joined in. The Mars Reconnaissance Orbiter used its HiRISE camera, normally employed for imaging the Martian surface in incredible detail, to capture views of the comet during the close approach. The Perseverance rover looked up from the Jezero crater and photographed the comet in the Martian sky. MAVEN, which studies Mars' upper atmosphere, observed from orbit. Even the European Space Agency's Trace Gas Orbiter refined the trajectory calculations using observations from October, improving positional accuracy by a factor of 10. The JUICE spacecraft, currently traveling toward Jupiter, attempted observations in November 2025. Data from these observations should arrive in February 2026 after being transmitted across hundreds of millions of kilometers of space. Amateur astronomers contributed too. Satoru Murata captured images on November 16th and 17th, 2025 that revealed jet structures. These jets pointed both toward and away from the Sun, with a collimated main tail and what looked like an anti-tail, which is an optical effect caused by viewing geometry. These amateur observations proved valuable for tracking rapid changes in activity that professional telescopes might miss due to limited observing time. Number 4, scientific significance. At number 4, the scientific significance becomes clear. Every interstellar object teaches us about conditions beyond our solar system. We can study comets from the Kuiper Belt and Oort cloud to learn about the outer reaches of our own system. But those objects all formed from the same primordial material that made the Sun and planets. Interstellar objects form somewhere else entirely, in different stellar environments with different compositions and histories. Galactic cosmic ray processing revealed by 3i Atlas changes how we interpret interstellar objects. Previous assumptions held that we would see pristine material unchanged since formation, giving us a direct window into extrasolar chemistry. Instead, we now know that the outer layers have been heavily modified. The original composition is buried deep inside, possibly kilometers down where cosmic rays can't penetrate. What erupts from the surface during activity represents this processed material. This has implications for understanding the formation environments. If a comet forms in a system rich in carbon monoxide, as many models predict, the carbon monoxide signature gets overwritten by cosmic ray conversion to carbon dioxide during the billions of years floating through interstellar space. To reconstruct the original composition, we need to account for these radiation effects. Comparing the three known interstellar objects shows an interesting progression. One-eye Oumuamua had an eccentricity of 1.2 and a hyperbolic excess velocity of 26 kilometers per second. It showed no clear coma or tail, leading to speculation about whether it was a comet or something else entirely. Its shape, inferred from light curves, appeared highly elongated or possibly flat. 2i Borisov had an eccentricity of 3.4 and a hyperbolic excess velocity of 32 kilometers per second. Showed a clear dust tail and cyanide emissions typical of comets. It even fragmented near perihelion, shedding pieces of its nucleus. 3i Atlas pushes the boundaries further with an eccentricity of 6.14 and a hyperbolic excess velocity of 58 kilometers per second. It shows clear cometary activity with complex jet structures and an unusual composition dominated by carbon dioxide. Number 3, speculation and controversy. Number 3 addresses speculation and controversy. Any unusual object from interstellar space inevitably attracts alternate theories. Avi Loeb, a Harvard astronomer, has suggested that some interstellar objects might be artificial probes from alien civilizations. For 3i Atlas, he pointed to the jet structures visible in amateur images as potentially indicating unnatural propulsion. The argument goes that if jets appear too symmetrical or too directed, they might represent thrust systems rather than natural outgassing. The scientific community generally disagrees with these interpretations. Cometary jets form naturally when sunlight heats specific areas of the nucleus, causing volatile ices to sublimate and create plumes of gas and dust. The direction of jets depends on the rotation state, surface composition variations, and heating patterns. All observed features of 3i Atlas match expectations for a natural comet. Carbon dioxide-driven outgassing explains the jet patterns without requiring any artificial mechanisms. Some social media posts claim the comet performed unnatural maneuvers or split into multiple pieces. Official tracking data through November 2025 shows no confirmed fragmentation events. The orbit follows a predictable path consistent with gravitational forces alone. While the jets do create small non-gravitational accelerations, these are tiny and completely consistent with how cometary outgassing affects trajectories. The phrase "new objects keep multiplying" in the title refers to the increasing detection rate of interstellar objects. Before 2017, we had 0 confirmed interstellar visitors. Then one-eye Oumuamua appeared. 2 years later, 2i Borisov arrived. Now in 2025, we have 3i Atlas. The detection rate is accelerating as survey telescopes improve. Projects like Atlas scan larger areas of sky more frequently with better sensitivity than older systems. The upcoming Vera C. Rubin Observatory will dramatically increase detection capabilities when it becomes fully operational. Models predict we might detect several interstellar objects per year once Rubin comes online. Number 2, future research directions. At number 2, future research directions offer exciting possibilities. Post-perihelion observations starting in November 2025 will track how activity declines as the comet moves away from the sun. JWST observations with the MIRI instrument can probe organic molecules and provide thermal mapping of the nucleus. Polarimetry measurements will refine understanding of dust particle properties, including size distributions and compositions. Longer-term, dedicated missions to intercept interstellar objects are being planned. The European Space Agency's Comet Interceptor mission sits in development, designed to wait in space until a suitable target appears, then launch quickly to intercept it. The mission would need to reach the object while it's still close enough to the inner solar system for detailed study. For 3i Atlas specifically, a mission launch from Earth would require a delta V, which is the change in velocity needed of at least 24 kilometers per second. Current propulsion technology makes this infeasible for rapid deployment. However, a mission staged for Mars orbit would only need about 5 kilometers per second, which is more achievable. Sample return missions remain the holy grail. Bringing back actual material from an interstellar object would allow laboratory analysis impossible with remote observations. We could study isotopic ratios, organic chemistry, crystalline structures, and trapped gases. This material would represent the only way to access stuff from another stellar system without traveling light years. The population statistics of interstellar objects remain highly uncertain. Models based on detection rates suggest there might be thousands of such objects in the intersolar system at any given time, most too small or too faint to detect. The question of where they all come from matters for understanding galactic evolution and planet formation processes. If every star system produces a population of ejected comets and asteroids during planetary migration phases, the galaxy should be full of these wanderers. Finding and characterizing more of them will test these theoretical predictions. Number 1, broader implications for astrobiology. Coming in at number 1, the broader implications connect to astrobiology and our search for life beyond Earth. Interstellar objects represent a form of panspermia vector, potentially carrying organic molecules or even microbial life between star systems. While extreme, this hypothesis has been considered seriously by scientists. Organic molecules created by cosmic ray processing in 3I Atlas include complex carbon compounds that could be relevant to prebiotic chemistry. The fact that interstellar objects exist at all shows that material exchange between stellar systems happens naturally. Any molecule synthesized in one system can be transported to others. This interconnectedness means that the chemistry of life might not be confined to individual stellar systems. If life arose early in our galaxy, material from those early biospheres could have seeded other systems. The age estimates for 3I Atlas place it potentially at 7 to 14 billion years old. This means it formed during cosmic noon, the period roughly 8 to 12 billion years ago when star formation in the universe peaked. Studying such ancient material provides insight into conditions during this crucial epoch. The elemental abundances, isotopic ratios, and organic chemistry all encode information about the stellar environment where the comet formed. Every new interstellar detection refines our understanding of what lies between the stars. For centuries, humans thought of interstellar space as empty void. We now know it's filled with dust, gas, magnetic fields, cosmic rays, and wandering planetary bodies ejected from their home systems. Some estimates suggest that rogue planets and sub-brown dwarfs drifting through interstellar space might outnumber stars. The galaxy is much more crowded than we ever thought, just with objects too dim to see from Earth. Looking ahead, as detection capabilities improve over the coming decade, the rate of interstellar object discoveries will likely accelerate dramatically. We may reach a point where finding a new one becomes routine rather than extraordinary. Each object will add to our knowledge base, building a statistical sample that reveals patterns and trends. Are most interstellar visitors icy comets like Borisov and 3I Atlas, or are rocky asteroids like Oumuamua more common? Do they come preferentially from certain galactic regions? What range of compositions exists? These questions can only be answered by finding many more examples. 3I Atlas represents a milestone in this journey. Its extreme velocity, unusual composition, and southern origin challenge existing models. Galactic cosmic ray processing evident in its chemistry rewrites assumptions about what we observe when we study these visitors. Rather than pristine time capsules from extrasolar formation, they are palimpsests, overwritten by billions of years of exposure to the harsh interstellar environment. Decoding both the original message and the edits requires sophisticated analysis and careful modeling. The story continues as observations accumulate and our understanding deepens, bringing us closer to comprehending the full diversity of objects populating our cosmic neighborhood.